The recording is on. Hi Arun, good morning. Okay, and great. Good. Okay, great. So, yes, okay. So, is my voice feebly audible to all of you? Are you able to hear me clearly? Okay, okay, okay. And others, only three people are able to hear me clearly. Arun, Jimmy, and Ajay. Iraya, Sizu, Rajkumar, Savita, Tranmin. Are you able to hear me clearly? So, okay, okay, okay. Great. So let's start. This is the second session of Big Data and Hadoop course. And in this session, we will go about first, we will recap what we had discussed in the previous session. Some of the details which are important, I would like to recap those. And then we will go about our environment overview, how to set up, how to start using a cluster. And then we will go about MapReduce basics. I will leave you with few questions which you have to come back tomorrow with your answers. Okay. And then we'll take up those problems tomorrow into details. Okay. Okay. Just a second. Okay. Some people are having little difficulty in connecting. So let me, because this is for them maybe second class, and for some it is a first class. Okay. Okay, just give me 1 minute. Okay. Hi. Okay. So, okay. So today I'm going to repeat a bit to all of the people what we are going to talk about today. Today we are going to discuss a bit about recap. Okay. Basically, a recap of the previous class where we will go about the architecture of the Hdfs and the task and job trackers. And then we will talk about MapReduce basics and environment overview. Okay. Okay. So again, welcome to No Big Data, and promote people to ask a lot of questions so that you have a clarity of the concept, and you do not get you always keep asking question at every slide. Okay. So this is okay. So this is basically a 30 hours class, 27 hours more left, and after that, there will be a project and there will be a 24 by 7 support. Class recordings will be available to you in your LMS account, which is sent to you. And we will provide cluster access so that you can experiment and even do your personal hobby work onto the cluster if you wish to you really handle the big data. And then we have various kinds of quizzes and certification tests. All right. So this is about me. For most of my career, I have been dealing with big data, but with respect to mostly building products or building solutions. All right. So I'm little rushing because we are around 10-15 minutes late today, and this generally happens in the beginning class. Okay. So these are the 10 sessions. The first session was understanding the big data and understanding basics of architecture, which we'll do the recap. All right. And this is today's class. Okay. So first of all, I'm going to discuss something called HDFS architecture. So the basic component, the most basic component from Hadoop architecture is HDFS. Now, what is HDFS and why do we need it? If you have lot of data, we are talking about petabytes of data or hundreds of terabytes of data. If you have hundreds of terabytes of data, you cannot store it in your standard manner using various kinds of hard disk to provide a great network file system. Most of the network file system succumb after 100 terabyte of data. They cannot provide a failover, great failover, great backup. They cannot provide a fast access to the data and very good load balancing and the division of the data on various machines. So HDFS came up with this idea. Basically, Google came up with this idea of Google file system where they have they have one master node and lot of data nodes. Okay, and in the similarly, so people from open source or people from Yahoo picked it up that paper and then wrote something called Hadoop distributed file system. All right, I'm sorry. So people from uh, open source and some people from Yahoo, specifically Dog Cutting and Mike Caffarella, they picked up that paper and then wrote equivalent open source system to the Google file system, and so that they can store very huge files and then they can read and write really fast. And to to make this possible, you need to have lot of computers in the network. Lot of computers in the network. So the first one is out of all the computers you are going to put in the network, one of them is is selected as name node. Generally, a computer with a lot of memory, lot of RAM in it is the name node. Name node is the master node, and then other computers, the smaller nodes, they are they are nominated as a data node. And what is the difference between the two? The name node, which is the master node, is the guy who is the bookkeeper. Okay, is the guy who is the bookkeeper. While other computers, other nodes, or will be using nodes, computers, machines interchangeably. Okay, so other nodes or other machines will be s- considered as data nodes. Their job is to read or write the data from the disk. All right. Now, whenever you have to write a file, say you have got 1 terabyte big file, or say you have got 1 GB size big file, you ask name node, hey, I want to store 1 GB file. Do you have computers available with you? And can you tell me to which data node should I be writing? And in response, Name node makes an entry that such and such person is trying to write data to data nodes, and gives out to you, hey, you go to these nodes and store your files, first block here, second block there, and third block there. Okay, so at the heart of the whole game, are something called blocks. So your file is split into smaller size of called blocks. Okay, blocks are by default 64 MB in case of Apache Hadoop, while 128 MB size in case of Cloudera Hadoop. Okay, but let's stick to the 64 MB size. And also, in case the RAM is low, your computer is running a low RAM, in those cases, the size of this block increases. Okay, and why does it do so is because if you have a smaller number of blocks, then there will be less number of data, metadata, which name node has to store. So name node essentially is nothing but a bookkeeper who keeps track of which block went to which machine. All right. So you take a file, you go to name node. Name node makes a book entry saying this file has to be split into these blocks and should be written to these nodes, and gives you those details to you and say, why don't you go and write this data onto these nodes, write this block there, this block there, and this block there, and come back to me and tell me if it is successful. Once it is successful, it makes an entry saying, hey, I'm done. All right. And similarly, name node basically keeps the name of the file, name of the block, and also the number of replication factor. In most of the cases, you want your file to be replicated multiple times because of, in case one of the node is not working or functioning correctly, then you should be able to recover your data. So the default replication number is 3. Okay, default replication number is 3, which means each of the block will be copied 3 times and will be stored on 3 different machines. Remember, uh, it doesn't store the backup of, or a copy of the same block onto the same machine. Okay, so these blocks are not equivalent to the file system blocks. They are, because file system blocks are smaller. Okay, they are in KBs, not in MBs. These blocks are with respect to your Hdfs, and this is basically decided by Hdfs which block, I mean, how big size. So each file is split into blocks, and each block is stored on one machine. All right, and each block will have multiple copies that will be stored on other machines, so that in case one of the node dies, the data on other machine is available. So if there was one block A, and this block got this machine on which this block was stored was dead. Now what does HDFS do in this case? It takes it finds out what all blocks were there on that machine which just went uh, haywire, the machine which just died. It finds out all the blocks on that machine as per the name node metadata. And once it finds out all those blocks which went missing, it replicates those blocks onto a newer machine. Okay. Or you can also look at it this way: to meet the replication requirement, which is 3 by default, it copies the lost data onto the new one. All right, because the lost data, only one copy is lost, you still have 2 copies. Okay, so that is the main crux of the HDFS. So Ajay Karthik's question is, what if the client dies after writing data without informing the name node? Very good question, Ajay. In that case, in that case, your data is lost. Okay. And client is also, because the client which was trying to write, it itself knows that, I mean, so the data is lost with the client. Okay. So generally, say you have a client, when we say client dies, it may be because of the connection, network connection is lost. It can, there could be hundreds of reasons, right? So in case you're, say you are writing, okay, okay, okay. So say you are writing to the net as to one of the data nodes or your client, which is basically you have these drivers, distributed file system drivers. They do this whole of job for you, talking to name node, talking to data node, and then writing to it. Now what happens in case a connection is lost? So the client which is trying to connect and write to data node will get an error, and it is up to the client whether to retry again or leave it as is, or check whether there is a better way of writing, or so when the client goes to name node gives a list of data nodes that you should write to these data nodes. Okay. So in case one of writing to one of the data node fails, you can try writing to the same node again, or you can inform name node saying I could not write to the data node, or you can start the whole process from the beginning again. So it is up to your client code completely. All right. Now another question we have from Arun is, how do we append file here? Okay. So if we have to append a file, okay. So most of the HDFS architecture is append only. Okay. It's mostly append only. In case you have to write or change any of the data, you will be writing that whole block again, and then abandoning the old one. All right. Now I'll talk about how do we append file here. So to append the file, you again ask name node, where is the block? All right. And then and then basically when you ask name node, I want to append to this file, and where are the blocks allocated? So in the return, it will give you that these are the blocks you need to write to. All right. In the meantime, it might have to do a rebalancing for you. Okay. So let's take a case of, you have so Ajay Karthik's question is still there. So let me first finish that part. Okay. So Ajay, before you report back to name node that you have successfully written to these nodes, it does not consider it to be committed. Okay. It will abandon that entry. Okay, actually, I will finish Arun's question first, and then yeah, it will abandon the entry completely. Now let me talk. So Arun's question is, how do we append file here? So we have got one file which is stored on one particular block. Okay, and you want to write some data. You want to say that please write this much bytes to the main to this particular file, and you tell that to name node, and name node figures out that the data you are trying to write exists in particular blocks. And in case you are trying to write data which is going to overflow the block size, it will suggest you that you write from this byte to this byte onto this block, onto this particular machine on this block, and this byte to this byte you write in another data node. So this is the duty of the name node. Okay. So you give a complete buffer to name node saying I want to write this thing, and then it will write that data. Okay. And even if you have to write, say, a smaller piece, but very frequently, then also you have to inform name node saying this is the chunk size, this is the buffer I'm going to write. Okay. It doesn't let you directly keep on writing to the data node. Okay. Savita's question. So was I able to answer your question? Uh, was I able to answer your question, Arun? Yes, great. So let me answer other questions. Great. And Ajay, was I able to clarify your doubts before I move forward? Great, great. And so now Savita's question, do you have one name node at all times or does it depend on data size? And if multiple, is the name node specified in the code or auto-detected? So it is always there is a one name node. Unlike most other systems, it is not really load balanced. Okay. But we have a backup of name node all the time available. As we as in terms of the consistency wise, HDFS says that we provide 100% consistency. And to provide a strict consistency, it needs to have a singular name node. Okay, not a load balance system. If there was a load balanced in case of name node, there was a name node 1 and name node 2. You can write to either of those things. That will become really a disastrous with respect to data, because to maintain a consistency you need to have a singular person. Okay. I mean singular node, and that is why a name node has been kept as single. Unlike most of the distributed architecture, it is most of the distributed architecture, everything is load balanced. But in case of HDFS name node, it is singular. But a secondary name node is kept for the cases when name node crashes, as well as there are something called backup name node, which which keeps on preparing themselves to replace name node. Okay. So Rajkumar's question is, what happens if name node? Let me answer. So feel free to write to all instead of only me, because everybody else will also get benefited by your questions. Okay. And let me just go through because these questions are scrolling up pretty fast. So that was Savita's question I was trying to answer. Right. So how does the failover happen in case of name node dies or gets corrupted? So name node maintains a transaction log on the disk as well as a snapshot of the data. In case name node went uh, basically name node got corrupted or something wrong happened. Now somebody has to either by the way of program has to replace replace this name node instead of the previous one on the same IP or the same DNS name. Somebody has to switch the DNS to point all the traffic for the name node to the newer machine. Okay. So that is a bit of slightly bit of manual intervention is required in this case. That is why some people like Hortonworks, they came up with an idea of secondary name node, which again is not 100% hot swap, but it is always there for taking the place of name node. All you need to do is all you need to do is change the name, uh, make the name of the newer node as the same IP as the previous one, or same name in case of you have a DNS. Okay. So this manual intervention is required. It's not like 100% immediately failover. There could be a difference of few milliseconds or few seconds or few minutes, up to how fast can you update your DNS entry, domain name service entry. Okay. Now let me answer. Okay. So Rajkumar's question was also the same as that one. Okay. So Ajay's question is, it's a very interesting question. In case of corruption, will the last bit be lost and restore to the last known correct snapshot? Very true, Ajay. That's how it happens. So if if there are clients who are writing to the data nodes, and this edit log is still in the memory that this person is writing to this one, that all data is lost. Okay. So the newer changes which are not yet committed to the disk are basically lost. Okay. So Savita's question is, how do companies like Amazon or Facebook handle this? So the news is that Amazon and Facebook, they have exactly same mechanism to handle this kind of architecture. But point here is that here we are dealing with the file system. Okay, here we are dealing with the file system. We have a great file system, and this backup node of name node is made extremely fast swap. Okay, this is made extremely fast swap. Also, name node, the chances of name node individually uh, getting corrupted or dying is very low as compared to the individual data nodes. Okay, so where do the most failure happen is at the end where the data is getting written most. Okay. So name node makes sure that none of the queries to the name node last for more than milliseconds, because it doesn't do much. It doesn't access the disk. It is mostly keep everything in the RAM. And that is why the fail chance of the the failure chances of name node are reduced a lot. There are the chances of name node failure are people try to keep the keep it as low as possible as well. People keep the backup node of name node ready, and the whole mechanism of writing to the disk is is such that in case name node is failing, so it should not be problematic to switch this, and that is done generally by the way of DNS load balancing or DNS or by the way of basically quickly swapping the DNS. So DNS backup is means in case you are trying to talk to name node and it fails. So now your client will talk to another IP address from the DNS. Okay. So those are the mechanisms taken into the account. Okay. So now, so this is how actually this is the possibly the best solution out there. Hdfs is the best solution out there for distributed file system. as of today. Because I was at Amazon and we had a similar system over there also. We just have different naming conventions. Okay. For secondary name node, is it almost consistent as primary name node? Okay, okay. Let me. So for Rajkumar's question is, for secondary name node, is it almost consistent as primary name node? So here I talked about two things. One was secondary name node, another was backup node. Secondary name node has has basically a little older data. Okay, it doesn't. It only has. So whenever a transaction happens at name node, it writes to the disk in the form of transaction logs, and those transaction logs are are available to the secondary name node, the backup copy of those, and secondary name node keeps on preparing itself to the almost the real time state. Now, now the moment the failure happens, there will be definitely a bit of loss, and it may not be exact in the exact condition as name node. So the most recent changes done by various clients might get lost. So this might sound that, oh, it's not really a tolerant, but if you think about it, if you think about it, there is only a rare possibility of data getting lost. Okay. Ajay Karthik's question is, then how do we notify clients? Okay. So we do not notify the clients. So the moment client is trying to access the name node after finishing the writing or before starting the writing, it gets an error. Okay. It tries again. And by that time, most likely your name node is up. So Ajay Karthik's question is, how frequently name node and secondary name node sync? So first of all, secondary name node is not exactly the mirror of the name node. Secondary name node is little bit of misnomer, but there is a backup name node which is specific to somebody called Hottenworks. It's not a public open one. I mean, it's not an Apache one. So that one is exact mirror copy of this one, and the sync keeps on happening frequently. Frequently, as in whenever some people are writing to the name node, it keeps on sending those changes to the other copies also, and they keep on applying those changes on their metadata. All right. So it is as frequent as it keeps on queuing those changes to the other secondary name node or whatever you want to call them. Now, Iraya's question is that how does how does division of file into different KB takes place? How does division of files into different size takes place? Okay, okay. Now let me talk about this. So basically, it's a fixed size file. So whenever you're asking name node that, hey, I want to store this file, it tells you back that these data nodes are available to store your files, and it also gives you back that block one has to be stored on these three machines because we have a three replication factor of three, and block 2 needs to be stored at this, and This division is done by your Hdfs client library. Okay, that's a Hadoop distributed file systems. Client is that's the role of that client. It talks to name node, then name node gives it back those files, and then from it starts writing to various data node from various bytes to various bytes. Okay, so this is how the division happens. So Twin's question is that why is replication factor 3 by default? I saw the same in Cassandra. Is there a reason? Okay. So the reason is generally that I mean uh, it's a basically you can say when you have a when you the chances of all three data getting lost, I would say it's generally arbitrary. We have found that having a backup factor of 3 is most safe possible because the chances of two computers, say you have two backups, the chances of both the computers failing together is extremely low. Okay, say let's say that every day the chances of a single computer failing. Okay, okay. I think I've lost some questions. Why don't why don't they come up with so HA means what do you mean by HA? Okay. So i- if you have let's say probability of one computer failing, okay, okay, of say 0.05 percent out of I mean how should I say at the chance of a computer failing is say 0.0001 at any point of time, and if you have two nodes the chance goes further below, and if you have three nodes the chance is multiplied, so which means that probability of the data getting lost keeps on getting lower and lower. All right. So in general, the three is considered a good enough. That's a general industry practice because all the three nodes will not get lost. So generally, two copies are maintained on the same rack, and the third one is maintained in a different data center. Okay. Or you can think of it that two copies are generally maintained in a single data center, and the third one is in another one. Okay. So there are various kinds of outage can happen, either machine level or the data center level or the rack level. So these are the three. So probably that's the reason there's a replication factor of 3 because there are generally three level of disaster that could happen. One is on machine level, rack level, or data center level. Ajay Karti, when failover happens, we switch to backup node, right? And some recent successful changes are lost. How do we notify client then? Will we read logs and try to restore the lost data? Right. So in these cases, as far as I have read with respect to HDFS and Google File System, there is no way to actually notify the clients that your data is lost. Okay. Okay. So those block of size there, but that's a very rare possibility. Okay. Because when the client is writing to the name node while making the change to the metadata, as well writes to the disk, marking marking that this client has written to this. So the chances of the data getting lost as because as soon as name node is applying to the metadata, the changes to the metadata, it's also writing to the disk, marking that this is the metadata, this is the changes, this is the transaction logs. So it quickly writes the transaction log to the disk, and that transaction log gets backed up to the secondary name node and elsewhere as well. Okay, so the chances of the successful data getting lost is very low. But in case a client has written to the data node and now it is trying to say there was a 1 GB file, client went on to all the data nodes and trying to write to the data nodes. And after finishing writing to the data nodes, it came back to name node. Now the chances of this phenomena is more because there is a lot of time has passed between first informing the name node and now writing to it. Okay. In this case, this whole information of the whatever client did just now is lost. Okay. So in case it goes back to the name node and says, hey, I'm trying to commit this, but this during this time, the name node has lost this information or lost some of the information that, hey, did you even try to start it? Or I mean, although that change will not be lost, okay, but name node is not there when it goes back. Okay, in that case, it has to either try again with the name node or we'll have to restart the process. Okay. Okay. So Arun's question and other somebody else's question is the same. Why don't they come up with high availability for name node with shared storage? Okay. So the thing is, name node is supposed to be the zero load system. Okay, zero load system, and it is anyway they try to keep it extremely high available. The only problem is that they want to have a singular name node because to have the consistency, to have the very strong consistency in because in case you have multiple or highly available name node, which means there are multiple name nodes catering to your requirement, they will have a different I mean, there is a huge possibility of inconsistent data. Okay, and that is why it is kept singular, but generally name node is by behavior is heavily available. Okay, and I mean, the only problem with name node is the failover. That is why we maintain the transaction log, and there is something called secondary name node, and there's a backup node. Okay, okay. So Savita's question is that in this peak there is one transaction where client is writing directly to the data node and not through. Okay. So see, okay, right. So Savita's question is that so so that's the crux of it. So when the client is writing, they write directly to the data node. If they are writing through the name node, then you will end up name node becoming the bottleneck. Okay. Client goes to the name node. Name node tells that these are the places you should go and write, and client directly writes to the data nodes. If client has been writing through the name node, then then name node will be always the bottleneck. So your read and write will be as fast as the name node's read and write. Okay, and or the network connection will choke. Okay, great. Now, Tranmin's question is that can you show what information does name node store? So name node store the metadata first of all, the name of the file, number of replicas, and basically I had my first slide. I had a first slide where okay. So just a second, just a second. Okay, and So, okay, okay, so we have, okay, so I mean, that information, like what metadata does name node store, is actually mentioned in the first one. I'll have to just hunt around a bit. Okay, just give me a second. Give me a second. So, right? So this is the kind of data. Now, is it clear to you, Tranmin, that okay? So name node contains, as I said, a file name, number of replicas, the block IDs, and on which machines does that block exist. Okay. So this is the name node metadata information which is stored there. List of files, list of block for each file, list of data node for each block, and then because each block will be replicated over and over to multiple machines, and then there is something called file attributes, okay, such as access time or replication factor. Similarly, there is another data which is stored on each name node is transaction log. Transaction log is written to the disk, which contains it records the file creation time, deletions, updation, everything. Okay. So hope you got your answer. Okay. So this is pretty much with respect to Hdfs architecture. Now let's move on and talk about this. Now, as a recap of what happens inside the execution mechanism, it's similar to Hdfs name nodes. So you have a master called job tracker who doesn't do anything other than delegation. You have task trackers whose job is to do the actual work. So job tracker is generally singular in nature. It maintains, okay. So let me recap what exactly is the behavior of a job tracker. Right now, when you think about job tracker, it is like somebody at the workshop, a manager of the workshop. You go and give your work to the job tracker. Job tracker sends the same work to three more people. Okay, same work to three more people on different data sets, and all I mean more than three. It could be any number, not really three. So it sends to multiple people that hey, get this job done, and these individual task executors or task tracker, they run your logic on different data sets, which are stored on the data nodes. Okay, so task tracker, so which means a job tracker is supposed to know about a job tracker is supposed to know about name node. So when you ask job tracker, "Okay, execute this," and this code depends on this input from this file. All right. Now job tracker will go and talk to name node, asking which all nodes have this particular file. And once it finds out that this particular file which is input to your program is existing on these data nodes, it finds out, job tracker's duty is to find out which are the task trackers located on the same machine or the near to the data nodes, the actual net data nodes on which that file is stored. And then it will ask those task tracker to execute the job for you. Okay, remember that each block or each block of your input file would be be stored at multiple places. Now when you ask job tracker to do something, it will find out of all the say three replications there, so out of all the three nodes, which one is most free, which one is not busy at this moment. Okay, which on that particular node will become your task tracker. So let me recap. So you have a lot of data to churn. You told job tracker that this is the input file for our program and I want to churn this data. Job tracker found out all the blocks with respect to this task with this input file, and where all this file is existing on which data nodes. And then correspondingly it found out for each block what are the task trackers which are most free, and the one which is closest and most free is given the job for the execution. And once that execution is finished, the whole data is merged together and presented to you. Okay, and this to solve this, there is something called map reduce mechanism. Now you can imagine that when you are processing the data on each block, each 64 MB data is getting processed by different computers, which means that how are we going to merge merge all of these computation together? It becomes a problem in itself. So it is fine to think of it like that we distributed the data, we distributed execution. How are we going to merge it? How are we going to what if my task tracker depends on data which uh, which exist in two different blocks? Okay, so I mean, say half of say you are splitting the you are trying to do some churning on sentence by sentence level. Okay, and half of a sentence is in one task tracker and half of the sentence is another task tracker. So those kind of details and complications arise when you do the computation. Okay, and on other than that, even if you are doing a very simple computations, how are you going to build your logic such that even if it gets distributed on different input sets, will it should give you the right results? Okay, so how do you divide your logic such that your logic gets replicated to multiple machines and still it gives the right result? So this it is a paradigm shift. How do you code such that the input size does not matter too much? Okay, so or splitting the input and executing your program multiple times on different pieces of input, it still gives the result as it should have given on a single node. So the number of input splitting uh, does not impact your logic at all. So how do you build such logic? How do you build a logic for which number of input pieces do not matter to you? Okay, so that is something which is done really well using map reduce paradigm. And for most of the class we'll talk about map reduce paradigm. So Ajay's question is, what is the parameter to say how free it is? How does it evaluate the current weight of a task? Example, let's say a task tracker is 40% free and tasks requirement is 50%. How is 40 and 50 is determined? Okay, so most of this is based on your basically the CPU performances. Okay, uh, on each machines. how busy is your CPU. That is one criteria. And so, and the other part which you should know is that at the because these tasks are executed again and again, so Hadoop also keeps track of how much time did it take last time. For this block size, how much time did your code take? So it keeps on tracking those records also, so that for the first time it might sound very inefficient, but next time, because it has figured out that your code for this big chunk size, your mapper takes this much time, and hence hence this is the requirement of your this is the CPU requirement of your code. So for first time, it will not be able to figure out how much time your code is going to take, but the next time it will do. So it keeps on optimizing those parts. So for a task node, Ajay's question is this chunk size always or quality of calculation? So it takes into both the accounts. For for churning of this chunk size by your mapper took this much time, and that is what is recorded with mapper. And next time when you are when it is executing the same logic, it will figure out and predict that this is what your mapper is going to take. Okay. Okay. So hope I am able to answer your question. Right. And then, okay, great. Very good questions actually. And right. So today we are going to talk a little bit about MapReduce in the second half. And so hope this is clear to you guys till now. Now let's move on. So uh, there has been a lot of hoopla about what is Apache Hadoop 2.0, Yarn. So basically, in a very simple words, we talked about just now this mechanism where any task is executed on multiple machines. Earlier, there was only one way of distributing the logic, that was MapReduce. But people realized that MapReduce is not the only way, and MapReduce cannot solve all the possible problems. And that is why people came up with a general task executor. Okay, general task executor. So Hadoop 1.0 contained something called Hdfs, and then on top of it there was MapReduce. Okay. Now any logic you have to do, you have to write MapReduce. So one guy from Yahoo came up, uh, and he said that why don't we make it very generic? Okay. If you have come up with a better paradigm, you should be able to use that one for other kind of problems which are not solvable by MapReduce. And that's what he came up with something called Yarn, cluster resource management. Basically, yet another resource negotiator is the name. And one of the implementations of Yarn is MapReduce. There are others also. There are one tool called for graph processing. It's called graph neo. I forgot the name. It's an interesting tool. And similarly, you could, if you come up with a system, if you come up with a paradigm which I mean, if you have a problem which cannot be solved by MapReduce, but you know how to distribute your logic, you know the way you can distribute your logic and talk to HDFS, then probably you should be building your own mechanism similar to MapReduce. And this flexibility was provided by Yarn. Yarn was just one step up from Hadoop 1.0. Okay. So but From the development perspective, nothing had changed. All the MapReduce jobs which was there earlier, they still work fine. All you need to do is just recompile it. So Ajay's question is, Yarn is just a plug or some other work? So it's actually a platform level change. It's a platform level change which made MapReduce and other paradigms pluggable. Okay, it's a complete platform level change. So MapReduce, instead of sitting just on top of Hdfs, it sits on top of Yarn. So the old MapReduce was basically was doing multiple things. First, it was also doing the execution, job queuing, everything it was doing. And how does a code go from one machine to another, and how does that execution happen? Everything was being taken care by the MapReduce. Now, most of it was generic in the sense that, say, loading of the code on each machine, keeping a queue, and all of it was very generic and could be used in other paradigm also. That is why MapReduce was split into two. One became Yarn, and MapReduce, as of now, is just one small part which uses Yarn. Arun's question is Yarn being used in production environment currently? Yes. Yes, because the movement to Yarn happened quite early. And also, since you did not have to change your MapReduce logic, since you did not have to change your MapReduce logic, and therefore people quickly adopted Hadoop 2.0. Okay, because it gives a lot of flexibility to people, and also it made it really efficient also with respect to resource management. So this is the difference between Hadoop 1.0 and 2.0. We'll talk about Yarn in details in the later classes, so you do not have to worry, because it has not impacted your actual MapReduce logic. If your code is your Hadoop, you're running on Hadoop 1.0 earlier, you can safely run Hadoop 2.0. Just that you will have to take out all your MapReduce jobs, recompile them, and push it again. Okay. So Twin's question is, so yarn is basically a way to distribute our programming logic. Yes, yes, you are very right. Programming logic or any kind of execution you want to do, you can use Yarn. But Yarn is not for the clients. Yarn is for the people who are developing things like MapReduce. So MapReduce sits on top of Yarn. All right. It doesn't impact us as the user any much. Yeah, everything else remains same, Gunjan. Everything else remains same. Okay. So basically you can say that you have a switchboard. Instead of switchboard getting dedicated to only fans, okay, now we have switchboard dedicated to other equipments also. So you can think of yarn as that way. Okay. So if I need to distribute my processing capability, it should be on yarn. So, okay, let me clarify this. So distribution of your program processing capability was possible with MapReduce also, but Yarn made it possible to invent newer ways of processing other than MapReduce. So, say for example, there are lots of problems which cannot be converted into MapReduce. Okay, let's say, graph algorithm, for example. Now graph algorithms cannot be converted into our, you know mm, into a MapReduce paradigm effectively. Say for PageRank, pay, Google PageRank, it is a complicated algorithm which requires you to traverse the whole page graph. Now this kind of problem takes a lot of code, or takes a lot of effort for converting into MapReduce. While there are other paradigms which solve those problems far better, and those can be parallel to what MapReduce does. So to facilitate all of such platforms similar to MapReduce, most of the common code from MapReduce was taken and split it into yarn. So it is basically, right. So it is basically, you know um, refactoring of MapReduce into two parts, where the common code of distributing the logic, taking care of the resources, as Arun was asking earlier about the resource computation, like, if 40% is this, 30% is this, what happens in this case? I think it was Arun. Okay. So, someone was asking, yeah. So those kind of computations are absorbed by yarn rather than MapReduce, because those computations are common for any distributed programming. All right. So this is actually a very logical step in the history of yarn, in the history of Hadoop. And this made it more powerful than the even the parent one was from Google, right? So Google came up with three papers. First was Google file system, then there was Google MapReduce, and third one was Google Big Table. Okay, Big Table is basically a database. So Google's MapReduce was basically Hadoop 1.0, and now Hadoop 2.0 is basically more powerful and more flexible than the parent one. Now you can have this another uh, graphics which shows you that what are the things which are possible. So, like for example, for batch processing, you use MapReduce. Then you have Apache Tez, which is interactive processing on top of Yarn. Similarly, you have HBase, which uses Yarn as well as might use MapReduce at various times. Then you have Storm, Apache Storm, everything. And then Giraffe is there. As I was telling you about the page rank, when you have to compute the page rank and you have to do lot of graph processing, like a Facebook network graph, those kind of processing could be done in graph. Then you have in memory processor, which is Spark, which does the distributed one, and so on. So there are a lot of such things were possible, and this was the logical step to take out common part of the MapReduce, name it Yarn, so that all other people can use it, all other plugins similar to MapReduce could be built. Okay. So this is general philosophy of Yarn. Okay. Or Hadoop 2.0. From the MapReduce perspective, everything is still exactly same. You do not have to worry about anything. It is just it's a say refactoring of the code. All right. Okay. So again, we will come back to Yarn again in the end of the session, because it's not very important to know it right now. Okay. Right. So I want to show you my cluster first. Okay. So there are two ways to access the cluster. What is wrong with this? Okay. And yeah. So first one is there's a Ambari project from Apache. Basically, it gives you a look into Hdfs cluster. All right. And so you go to hadoop1.nobigdata.com 8080. and I will be sharing with you the password of this one. I think I have already shared. Right, right. So, right. So these are this is my cluster where I have various kinds of products installed. This is my HDFS. HDFS is saying that my secondary name node is stopped. Okay. And we have name node is started. Data nodes, there is only one data nodes because we are adding more data nodes. We are adding more data nodes to it. Okay. One by one. And then this is the status of the yarn. And then we have map reducer. It says that history server is stopped while map reduce client is there. Map reduce clients are there. Similarly, all of this, or you can see the status of all of this on online. Okay, so we'll be adding more server. Right now, only there are two servers. Okay, so you can see the dashboard and there are these hosts. Okay, so we have Hadoop 1.nobigdata.com, Hadoop 2.nobigdata.com. All right, and this is the one. I'll be sharing with you the user access to it. How do you access it? And all right, okay. And then other than this, we have something called hue, which helps you talking to the components individually. Okay. So it shows you the interface to various products. Right. So Gunjan's question is that can we be able to set such an complete arrangement for our own individual usage? So the problem is that if you either you have to buy multiple machines to set it up. If you load a single machine with all of this, then it becomes a little tricky. Although the Hortonworks machine is good enough. Okay, so in the installation manual, we have mentioned that you can set up your own. Okay, so this is where you will be writing scripts also. Okay, so this is one way to interact with the components, and the file browser is giving some errors. Yeah, so we working on that. So basically, there are two ways to interact with. Right. So Gunjan's question is, can we have so do not worry about this because I'll be giving you the complete access to this cluster so that you can experiment on these nodes. All right. So this was a brief look at our UI from Ambari and Hue. Okay. So we have something called Hue, which is runs on 8000. Okay. Okay. And all right. So this is Hue and Ambari. Now, this was just a UI. Okay. Now the real stuff. So, okay. Yeah. So again, Gunjan's question is, we can have a multiple Amazon EC2 instance. Yes, yes, you can have that. You can have that. Or if you want, you connect with me if you're really interested in setting up your cluster. You let me know. I have some servers left over. Okay. You can use those ones. All right. and or you can use this cluster itself. We are extending it. Okay. Now you so other way, first one I showed you that there is something called Ambari. Using Ambari, you see the status of all the services, what is running, what is failing, and everything. Right now we have two nodes, and we are adding more nodes by the end of this week. Okay, we already requested them. So by end of this week, we'll have some more nodes into this, and as the load increases, we will keep on adding the nodes into this. And other than this, what you can do is you can basically take up. Let me open the course page for you. Not this one, not this one. My courses, and we have right. So this is the installation instructions. So first way, easiest way is to using the cluster. Hello. Yeah. So first way will be using the cluster, and second way will be using the SSH. Okay. SSH login passwords are available here. All right. So let me just show you. So I'm doing SSH student at hadoop.nobigdata.com, and all right. So this is the SSH server we have. Okay. Now to do your work, you create a folder here. Say I will create my own folder. So this is the local machine, and there is another place called Hdfs where you will be uploading the files into, right? So any work I do, I generally uh, do it in my own folder because there will be multiple people who are going to use it. So you can see that this is the folder which contains all of will contain my files. Similarly, there are other persons like Gaurav, Shashank, Sukhsavat, and other people. They have kept their data locally in a different folder as well. Similarly, I'm just doing some. Okay, so this is my data. Now if I have to, as I told you, if I have to interact with the HDFS, i will I will use a command called Hadoop. Okay, Hadoop, and then say file system and then ls. So it's now talking to name node, and will getting the list of all the files, and this is the folders which exist on the name node. All right, or we can say ls this. Okay, so this is how the HDFS looks like. These are the folders existing in HDFS. Okay, and so basically what you do is go to users folder. In let's see what is there in the users folder. Okay, so in the folder called student, not student, instrument, in the folder called student, you will be creating your files. Uh, just a second, just a second. Right. So in the folder called student, user/user/student, you will create your folder, say as Giri1. So to use HDFS, you say Hadoop space fs, and then you start writing command. To see what are the commands possible with respect to Hadoop, you say simply type Hadoop, and then you see these all the commands, and then you say Hadoop help fs, not this, Hadoop fs minus minus help. Okay, so you will see, just a second, yeah. So you say Hadoop minus minus help. It shows you the detailed list of all the commands. How do you do? And then you need to remember few commands. One is ls, other is make directory. Ls shows you the listing of files, and make directory makes a file, and say here we are trying to say make directory user slash student slash sgiri1. Okay, now it's creating the directory into her hdfs, and then I say minus ls. Okay, so this shows us the folders. And if you have to copy any data from your local drive, local as in Hadoop one's local one. So Hadoop has got two places. One is your local one, local Hadoop, local disk, and there is a HDFS. HDFS, anything you put it in HDFS will get copied onto data nodes. All right. Now what I do is I say Hadoop FS, meaning HDFS. Now I say copy from local, and my local file's name is ml-100k.zip to user dot student slash, and that's it. Okay, user dot student sgiri1, that's my folder. So it will copy ml-100k.zip onto there. So now it's pushed onto the hdfs, and then you can see. All right. So it has been uploaded now. You can start churning it, or if you want to copy the folder instead, you can do the copying of the folder also, like this. Okay. So now, okay. So this is what it is. All right. Okay. So so these are the two servers, and there is an independent individual server also, which is Hadoop 3. Okay, which has not yet joined this cluster. Okay, so that is kept separate one, just for people who want to experiment on the individual machine. Okay, and yeah, so this is how you are going to use it. So this is how you log into the cluster. And those people who do not also, at various circumstances, you have to use, say, your local machine. Okay, you want to just experiment locally. In those cases you can download first of all a virtual machine from VirtualBox is pretty good. And then you download a Hortonworks virtual machine. I was earlier using Cloudera, but I found Hortonworks machine more complete than the Cloudera one. And Cloudera one is a little more clumsy than this Hortonworks one. So I've started using the Hortonworks because it has all the components, and all the components are, and it runs very well on the desktop. Okay, because it doesn't take too much of memory and all. Okay, and remember to before starting up, y- so virtual machine. Okay, okay, so here you can use these. Okay, and once you are finished with Hortonworks, installing the Hortonworks machine, this is the one. You go to the Hortonworks, and then start downloading it, and then that's it. All right. And after you are done with it, you go to your local your computer, and say 8000, and you can see Hue working, HUE, and there you start doing your operations. So these are the two ways, but I strongly recommend that you learn how to use our cluster. Okay, that will make life easier in the sense that we will be able to debug problems better. All right, and and that will help both of us too. Now, I want to take a little break. So, I I mean, let's take a 5 minutes break and then come back in 5 minutes. Okay. 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 Let's take a 10 minutes break then. Great. Okay. But just that we'll have to extend by 10 minutes after 10 o'clock. 10:10 till 10:10. Okay. Okay. Hi guys, I'm back. Are you guys back? Okay. 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 So Gunjan's question is that um, in the actual development, maintenance, production scenario, how the setup will look like? Okay. 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 So okay. Okay. So okay, Gunjan, I'll answer to you your question. So his question is that do we have to set up different machines for different kind of use cases, whether testing, development, maintenance, production, or do we set up different clusters for all of these? My answer is no. Y- Yes, Tuhin, you should be using Hot&Work Sandbox because I found Hot&Work Sandbox better. All right. So this is a very interesting question Gunjan has asked. So if you have a development, test, maintenance, production kind of area, do you set up different clusters for different use cases? The answer is no. The answer is no. Okay. So basically, the at max, what you can do is you have one main cluster. You have one main cluster for the production environment, and you just keep a smaller one, say 3 nodes cluster for testing, which you give to various people for 3 nodes cluster. And most of the local testing people can do using the local machines for most of their job. But when you have to test whether how is it performing, how is your code performing in the distributed environment, if you just have to test that part, in those cases you use a separate smaller cluster, say 3 nodes cluster. But the main intention is to have a central singular cluster on which you divide the file system directories such that few directories are only for production while few are all for the other nodes. Okay. Right. Yes, for performance testing actual cluster is generally preferred, or for normal your program you should generally be doing it on the desktop based. Okay. But here, whenever you are putting anything on the cluster, you should be doing a good enough work. It's your code should not be something which really hurts the other processing. So that is why those kind of issues are resolved. And also Hadoop anyway will figure it out whether you are hurting the cluster or not, and your job will get killed. Okay. If you there are something called quotas which you can fix on each node for each job. All right. Okay. Yeah. So Tuhin, I did not get your question. I have 8 GB core i5 machine. I can set up 2 clusters here. No, I think it will be too much to ask for the for that machine. Okay, because for two cluster you need to. Okay, let me. How many physical machines EC2 instances will be required? It will help me decide and justify the expense. So the minimum number of machines which are required to set up the cluster are two. Okay, and rest is up to your load. Okay, two or three, probably a three would be better. Okay, so minimum you should keep as three, and then you scale up, right? And it all depends on what are the kind of things you're going to do, because there are many services starting with Pig, Hive, Hbase, and Storm, and there are all sorts of things you can run. So that is why it is okay. That is why it is required to have at least minimum of three machines. Okay, okay, great. Now let's move on. So okay, so yeah, let me have a look at. Okay, so everybody is in. Great. So we have shown you that how to copy from command line. Here there will be a little bit of confusion because there are two places. First you SSH into, say you have a file onto your desktop. To take it to Hdfs, it's a two-step process. You first copy that file onto hadoop1.nobigdata.com. From there you push it to the Hdfs. Okay. And now let me have a look. I don't know where have I kept all of this. Okay, so these were just for the demo. Okay, 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 okay. So now, I mean, I want to give you, because right now I do not want to give you a demonstration of MapReduce. I think we can give a demonstration of MapReduce in the next one. Okay, because yeah. So the main job is not done, right? So now let let's start the second part of the discussion today. First part was how to set up and how to the recap of the previous one. Now the very important aspect, which I'm going to take 2.5 classes just on the topic called map and reduce and thinking in terms of map and reduce. Okay, this is probably the most important session. Okay, and even if you have no programming background, stay stay connected. Do not give up here. Okay, because this is I'm trying my best to convert any problem into non-programming thing in case of MapReduce. All right, and this is a little different way of thinking per se. As I had explained earlier also, that the probably the most common paradigm as of today for distributed programming is map and reduce. And programming language such as Hive or Pig Latin, they all internally depend on MapReduce. Similarly, your HBase and all other component, they use MapReduce at one point or the another. So using a MapReduce or understanding a MapReduce becomes inevitable for all of us. Whether you are administrator, or whether you are analyst, whether you are a data scientist, or whether you are a Hadoop developer, all of you, one time or the another, you will be thinking things in terms of map and reduce. Okay. And I mean it will not be too much of difficult thing to do. It is just that it is the just that when we look at a programming language, or when we look at a programming language and we are not aware of that programming language, we generally get scared of it. Okay, so I'll try my best to keep it extremely simple. Okay, now let's jump in. So first job, in case of MapReduce, the first example in case of MapReduce I'm going to take is a simple word count problem. In this problem, you have got a huge text, huge English text, and you have to find out the frequency of words. Which word is how frequently has occurred. It's as simple as that. Okay. Now, remember that it's a huge text. Maybe it cannot fit into the computer's memory in one go, but on the disk, when I say memory, it is always RAM, and disk means your hard disk. It can be SSD or it can be hard disk, normal hard disk. All right. So it's a huge text. Say let's imagine it to be few GBs. Or if you had to do it for Wikipedia, it would be huge. So now the question is, given a huge text, how do you count frequencies of the words? Which word has come how many times in this text? What is the occurrence? How many times a word has occurred? So let's just start. So in the simple way, even without in your daily life, in your normal way of working, how would you do it? How would you do such kind of thing? No, I'm expecting answers here. Okay, anybody? So just feel free to just drop a line or two of your strategy, and that will be sufficient. So you're given a huge text, a corpus of text, and you have to find out the occurrence, number of times each word has occurred, or the frequency of words. Okay. Okay, Gunjan, feel free to write your answers to all of the people. Okay, it is okay. All right, because anyway we are all going to be together for say for this course 1.5 months. All right. Great. Arun's answer is that create a hash table for different words as key as the words, and the value as count. Perfect, perfect. Okay, so basically we are starting to count words, and the general way is to have a hash table. In that you put the key at the word and then value. It is equal to saying that you are creating a dictionary kind of a thing, where instead of a meaning you have only counts. So every time you see a word, you put it into a dictionary and say it's a mark, then mark it with a count. Then you see another word, locate that word in the dictionary quickly, and then mark it, and so on. You keep on doing this again and again. Okay. Tran means answer is really interesting. He says that he will use Lucene index. Great, great. And yeah, but in very simple words, if there was no Lucene, there was nothing. What is it that you will do? Okay. So question is that given a list of words, given a huge plain text file, how will you find the frequencies of the words? And Gunjan's answer is create a list of words to be searched and then start looking for them in the data. That's also a good approach. But we don't know the list of the words, right? We have to prepare this list as we go on scanning the text. All right. Right. So Anybody? Just any random idea. It'll be good actually to have. So Ajay's answer is split every line. Good. And parallel process. Good. Good. Any other? Okay. Hash map key is word and the value is count. Good. Good. Great. So let's look at the first answer. All right. The programming approach is that create a hash table. Hash table is, you can think of a huge two column Excel sheet. All right. I mean, or you can think of an array where the key is a number. We have found out a way to convert the whole word into the number, say summing up all the values of each character, and that is stable, as in we can quickly jump to that word and find out its frequency. So we have created this table where we are marking each word that this we have found, and the frequency is this much. And then for each word in this file, you keep on scanning this file, pick up word by word, and then update this table. Okay. So this is the general way of solving a word count problem. Okay. So once you are done with scanning the files, you just print the hash table saying this is what it is. So you found a word, you put it in the dictionary or a hash table saying its frequency is 1. Then you picked up another one, you looked up in the dictionary if you have already found it or not. If you have already found that word, then you increase its frequency. If it is not found, then you add it to the dictionary and say the frequency is 1, and so on. So this is pretty straightforward. All right. So so who did not get this approach? So we created a big dictionary, or you can, if you have to do it yourself, you read word by word, mark and mark in a dictionary that this word I have encountered and its frequency is this much. All right. And why I'm saying dictionary, it is very, very quick to locate a word in the dictionary because you can jump quickly. All right. Similarly, in a hash table, it is very easy to find out whether the word has been added or not. Very quickly you can jump to the word and its value. So hash map is one very, very important data structure, okay, which is basically key value pairs, where you can jump to the key or jump to a value of the key in a very, very fast manner. The only downside is, yeah, can anybody say the problems before I say downsides? So who did not get this? I can. Yes. What if the data size is huge? Okay. Yes, yes. So if memory is required, so loading it as, so that if your dictionary keeps on growing big, since as we told that hash table is, you can keep on jumping back and forth, and it has to be kept in the memory. Random access memory is the reason, right? So hash table is you can think of that in case your RAM, because it is, hash table is kept in the RAM, okay, and if it keeps on increasing and RAM is always limited, okay, great, great, and loading it at one go will be a problem. Excellent. So the simple ways cannot process the data beyond the RAM size. All right. Okay. Now approach 2. There could be, I will take up one approach by approach. So should I move on to the next approach, or do you have questions with respect to this approach? Feel free to ask. So we are talking about computation, and computation in particular, it's MapReduce here. All right. So In the programmatic approach, where we have to count words, what we have done is taken up each word, put it in the dictionary, and increasing the value. Great. Now let's look at the second example. Second example is that what we have done is we have broken the lines into words. Okay, and we are inserting words into a table. All right, we are inserting words into table. So we have got a, basically a single column in the table in which there is the name of the column is words or word, and each column contains a singular word, and we broke the text into each word by word. So we are reading this text from top to bottom and from left to right, and as and when we hit a space, we take this we hit a borderline of the word, we take this word and put it into the database. And now once we have finished scanning the data and putting into SQL, we do select word and count star from table and group by word. Okay, so what is the problem do you see here? Anybody? So did you get this approach? Here we are utilizing Microsoft SQL or any Oracle SQL or any other SQL database to do the counting for you. Okay, do you see any problem with this approach? Gunjan says it will be huge database size and group by will take a lot of lifetime. Yes, yes, right. First part is to read the file and then put it into database. Yes. So in case you are using a single computer, you are limited by that computer's hard disk. How fast can you read it? Okay. And hence both the things, your hard disk speed, your database uh, performance, and your processing power will all become the limitation. All right. Now another way is great. And moreover, most of the databases suffer from inability to index when I mean sloppiness in the index when the data grows big, and this is one such case. So Iraya's question is, how will you break the book into words? So what you do is, so you have got a plain text. There are few ways to break into words. First one is using say line.split command from the from Java or from any other programming language, or replacing space by a new line. Okay, if you replace the space by a new line, so each line will now contain only a single word, and then you can go ahead, or you can do you can start reading characters. The moment you hit a space means you have reached a word. Okay. Vijay is saying, can we do partition based on alphabets? Ye- yes, that we can do. But then again, for each alphabet, say your A, B, C, and all that, you are going to have further more words. Okay, and basically, what you are suggesting is that are you suggesting that for each letter we keep a separate file? So if you do that, how are you going to count? So are you going to scan this file one by one and only first count all the words starting with A, then in the second pass you count all the words starting with B, and then in the third pass and so on, in 26 passes you will be able to count frequency of all the words, right? by minimizing the RAM. But that's a good approach, and that's a very good approach for splitting the data. And that is one way to also divide the data in case it's not fitting into RAM. All right. Now, now there are multiple problems with that. First is it is slow in the sense that every time you do that, you are going to end up with, okay. So let me repeat that approach again, what Vijay was suggesting. Although he was suggesting maybe something similar, I was asking. So the approach was, since our whole data was not fitting into memory, the whole hash table was not fitting into memory. So we said, let's just first count all the words, only the words starting with A. All right. And so we scan the whole text one word by one word, and first count all the words. We keep only the words which are starting with alphabet A, and keep that into hash table, and then count those, and so on. All or we create 26 different files out of this plain text. Okay, we open 26 files parallelly, and we put the words one by one. Say we create 26 files A to Z, and all the words starting with A we put it in one file, all the words starting with B we put it another, and C into another, and so on, right? Now problem with this approach are multiple. First one first one and then you repeat this first approach which we just described in the same manner. Okay, the first approach where we were counting the whole dictionary, so he has partitioned the problem into smaller. It's a good way to do solve most of the big data problem. But here the problem is that whenever we are dividing the data, there are high chances that still words starting with a particular letter can overflow your memory. Okay. Also, splitting the data on a single machine is a very, very painful task, because you are going to use the same disk limitation. A disk has a huge limitation on reading. You cannot read or write in parallel. There is only single header which does the reading writing for you. Okay. I mean, writing head, not header, writing head, the one which writes onto the disk. So that is why you'll be limited by first RAM, because you are not sure whether all the words starting with A are going to fit into the RAM or not. Second, the hard disk will become your bottleneck when you are reading writing from it fast. And also these will be all sequential operation. It will take a little bit of time. All right. Okay, great, great. This is a good. We talked about two different approaches, three different approaches. One is loading whole file into the memory, a- and uh, and creating a hash table, basically in the creating a hash table and keeping that memory and counting it. And second approach was to dividing this data into smaller chunks based on the starting letter. Okay, all right. Now let's have a look at the second approach. Do you see any problem with this approach, SQL approach? Okay, now we will come back to the first and second approach. Now there is third approach. All right, there is third approach to solving that problem. Okay, so generally, whenever I'm thinking about when I'm talking about most of these big data problems, most of these problems can be solved in a lot of ways. Okay, so you should keep your mind open to every solution to of the problem. So let's talk about approach number three. Okay. In this approach, it's a very, very simple Unix command. In this approach, what we did first was replaced, replaced, you can see this. So first, all the books of Lord of the Rings, I did concatenate all of those files and printed it onto the standard input. Okay, so who is not aware of Unix pipes? Okay, so let me just go this way. Here, this is my Unix way. It is pretty simple way. Okay, okay, okay. So Unix pipes, this pipe you see, this pipe, it is basically connecting this command and this command. There are the chain of commands. One is cat concatenate, then this sed, then sort, and then Unix. These are all independent commands. The pipe connects them together such that the output of the first command, this is the first command, becomes the input to the second command. Okay, so the output of cat file 1, file 2, and file 3, and so on, the output of this will become the input to SCD. Okay, and now SCD will read that input and do the replacing of tab. It replaces the tab with the new line. Okay, tab or space with the new line, and hence it will convert the whole file into such that each line contains a word. SCD. No, I'm not using the Unix command. I'm just explaining from the UI, from this. Okay, so we have. So what does cat do? Cat just concatenate all the files, whatever you pass as the command line argument, file 1, file 2, file 3, and so on, and gives it to the standard output. If you don't put anything of this, if you just type this, all of this text will come to your screen. Okay, now since you have done SED, you can think of SED as control F. Control F means replace a text with some other text. Okay, here I say SED substitute this text this text with this text. What does this text means? It is a regular expression. Regular expression means that is a pattern which says slash tab. This is slash t means slash tab, and the space, and then plus any number of tabs or space. Any number of tabs or space will be replaced with a new line. Okay, it is like going control F into a text file, and wherever you find a space you replace with a new line. Okay, it is like you going into a text file, and then you saying at every space in your file you delete all the space and press enter. That is what this command is doing. So at the end of it, you will have a huge file. You'll have a huge file containing one word per line. Okay, one word per line. All right. Now, what all this list of whole words, it will contain the whole text or the book into the list of words. Here, we are not taking into account the things like, the things like hyphen at the end of the line where we say the word is continued to the next one. All right. We are not taking those kind of. It is considering that basically replace all the space with a new line. All right. Then whatever is the, now we got the list of words, if we sort it, now, okay, it will arrange all these words into an increasing order. Okay, so this command, when it is you use this command, right? So it doesn't matter for Unix to what kind of size the file is carrying. All it does is it takes all the content and gives it to the standard output or to any other program. Okay, so it's not our problem. I mean, it will be Unix's problem of considering the sizes. Now let's have a look at the sort command. All it does is whatever list of things it is given, it will order them line by line. Okay, it'll go from left to right and then keep on ordering that. All right, and then thankfully there is a beautiful command called unique in Unix. If you say -c on that, it will just count the frequencies, provided the input data is ordered. All right. So before MapReduce and Hadoop came into play, this is how most of the Unix hackers used to do things. Most of the Unix programmers used to do things, handle the big data. So this is what most of us had been doing before 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 Hadoop came into play. All right. And I'll talk about a little bit later that this portion where we say sort can be here it is sorting based on the disk. All right, when I say minus m here and say there are different sizes, so if I say 20 MB, say 2 GB, let's say 2 GB will only use 2 GB RAM. Okay, and rest of it will be disk sort, because sorting becomes difficult in the memory. All right. So here what I did was I created first of all a list of words, then ordered these list of words, then went from top to bottom and just counting the words which have come together. Okay, which have come together. Because if you sort it, all the words will come together, and the moment you encounter a different words, you can print the frequency of the previous word. Okay, you went from up, and then till the moment the word changes, you keep on counting, and then the moment the word changes, you print that this word occurred these many times, and then you reset the counter and start from counting from 1. The next word, when you encounter the next word, you start again counting from 1, and so on. So it's a very simple thing. If I can show you that this is how you count the words, you will laugh at me, right? So so concatenate all the file, replace space with a new line. Now you got a list of words, pass it to a command called sort, which will order these lines, and then you pass it to unique minus c. Unique minus c is nothing but you go from top to bottom, counting the occurrence of a word in a sorted file, in an ordered text. So this is another approach other than SQL. All right. Now we talked about the problem with respect to the SQL code, and similarly, there are problems with both of these approaches. Okay, so quickly, can somebody summarize that what are the problems with approach 2 and 3? Approach 2 was using an SQL where we said select this word and count the frequency. Okay, and approach 3 was using Unix where we used a sort command. All right. Can somebody just quickly answer me? So here, problem 2 was SQL, and approach 2 was SQL, and approach 3 was Unix. Yes. So memory in case of Unix and SQL, the memory is taken care. When we say sort minus SG, it does it into 2 GB. Yes, it takes a lot of time and is sequential. Excellent. All right. The moment data starts going beyond RAM, and the time taken starts increasing in a disproportionate way, the following will become bottleneck: the disk speed and space, network speed, RAM speed and space, and CPU. All of these things will become a problem, and then it hangs. Yes. Okay. So this is one approach. These are the approaches. Now, all right. Yeah. Once while parsing and other while counting. Yes. We are looking for the words twice. Good. Good. So we can actually minimize all of that or do a distributed computing. And now let's have a look at the distributed computing way. Okay, this is the fourth approach, and this approach is also known as distributed sort. So what does a external sort or distributed sort means? It means that split the file to a size that fits a RAM. Okay, and then you you send all these chunks, all these blocks to multiple computers to get it sorted, and then you can merge them using a command called sort minus m. And merging multiple sorted files into one is easier task than sorting all the files together. Okay, is merging sorted text is actually easier. Okay, you can imagine that there are two queues of people who are arranged by their heights. All right, there were two queues in which each of the queue is containing people who are standing by the order of increasing the heights. Now you have to merge these two queues together into making one. It is very easy. You first of all, you as the guy who is counting the, I mean merging the file, stand in front of the line and take the first two, and whosoever is shorter, keep him ahead, and the second one, uh, and now you take the next one in the queue who is shorter, and so on. You keep on doing this again and again. You picked up first two. Okay, out of these, whosoever is shorter, you put him into the freshly created line. So this, and then from the line which you have picked up the shorter guy, you pick up the next person and compare with the other person. And now out of these two, whosoever is shorter, you take him and put him into the another queue. This is how you merge two queues which are sorted in the physical world, and this is how exactly you can merge sorted text into a single one. Now there could be two approaches here also. First one, the way Ajay was saying that, I think Ajay was saying, I forgot the name. Ajay was saying that we create a queue. Sorry, Ajay was saying that why don't we split based on first letter. So while dividing this data, we can also upfront divide the data by those kind of things, first letter, right? So this is another way. So you what the external sort, what we have done, we took this huge text of file, and then we divided this data, divided this whole file or text into number of lines, 100 lines, 100 lines, or say 10,000 lines. So each 10,000 line we send it to different machine and ask all of these machines to give the frequency. Okay, and sort. Or here, the approach which I'm trying to show is that we have created these lines and given each to all the machines and let them give me the frequency. Okay, so here there's a user here. User has asked machine 1 to to do the to do the counting on a list of words called sa re re, and machine 2 ga ga re. Okay, and then both of these machines are returning the frequency. First is saying the frequency of re is 2 and sa is 1, and in a increasing order. Okay, increasing, not increasing order of the counts, but increasing order of the alphabet. So R comes first, S comes later. All right, and similarly machine 2 gave back ga has come twice, re has come once. Okay, now this user who has asked machine 1 and machine 2 will combine these together, and then ga is 2, re has come 1 plus 2 3 times, and sa has come once. So this is how we do the distributed computing way. Okay, we asked both the machine to prepare the frequency table for us, and then we merged it. Okay, so sh- should I explain it again? Okay. Yes. Savita is saying that in this case there is no pre-ordering of the words. You are chunking out the work upfront. Yes. So we did not do any of our intelligence by ourselves. We just sent the text to both machine 1 and machine 2. Okay. Let them divide it and do that. So why did we even have to sort if we are giving sums? Okay, why do we have to sort if we are giving sums? Because when this user is merging it, machine 1 gave it back, machine 2 gave it back. Maybe the same word exists at both the places. The way Ray has existed at both the places. Now if the user again have to sort both the words together to merge it, then it will become a hell lot of work for the user to do that. And that's what the problem we were solving, right? So what am I, so what I'm saying, so Ajay and Savita is probably they're asking why exactly, Tuhin, you got it right. So right now I'm just talking about the approach before MapReduce came into play. All right. So what this user did was splitted the files into 10,000 lines each, gave to machine 1, machine 2, and so on. Let machine 1, machine 2 run the algorithm, which we talked in the first uh, first approach, which was programmatic way. Let machine 1, machine 2, and so on, all of them use the same algorithm and give the result back to the user in the order of alphabetic order of the words. Okay, now user will take all of these files together and will merge it and prepare the output. Now somebody's question was, why does machine 1, machine 2 needs to give the words in order? Because that makes the life of user easier. Otherwise it becomes a very difficult task to again merge. All right, because as I gave you the problem that if you have two queues in the physical world, you have two queues of people. Both of these queues are people are ordered by their heights in the increasing manner. The first one is the shortest and the last one is the tallest. All right, now you have got to merge these two queues. It is very easy to merge these two queues, right? You just take first two and then keep on doing that. Okay, yeah, it is like merge sort, or you can think like a heap way. All right, so take first 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 word from each of these machines and then compare which one is shorter, smallest out of all of these, or where all it's being duplicated, and then you take this and print out the sum. That's pretty easier to do. Okay, so was I able to explain this approach? Because this is very important approach. I delegated all of my work to all the other machines and then merged it all together. Okay, so this is the approach we use it. We used it before MapReduce came into play. Do you think there is a problem with this external sort? Anybody? Yes. So hardware capability of each machine might be different and you don't know about it. That's a very good point, Tuhin. Yes, that's a problem. Ajay's question is answer is, if it is very huge data, then you need so many machines. Yes, but that's not a problem. But that's okay. That anyway you will need so many machines. The workload is not known for each of the machine. Very good point, Savita. Yeah. How would you divide the work? And similarly, the good point is that now you had a problem of storage earlier, right? The same file you are trying to sort right now or trying to process, if it is huge, you had a problem of storage. So you in HDFS you have anyway kept it on HDFS where the chunks are divided. And why don't why can't we utilize this property of already divided files? Here we had to transfer this data again to all of the to all of the machines. We had to transfer this data. We had to send this, and I mean, this data transfer could be saved because any if we can anyway store our file system onto multiple machine, then we can instead of again sending the data, we can just send our logic and then get it executed. Okay, that is another benefit, right? So Savita, we are not here when we are sending the data, we are not doing any kind of distinction. We just take first n number of lines and dump it to machine 1. First next n number of lines we dump it to machine 2. We are not sending it based on their alphabetic manner. All right, so that is why, so that was the previous approach we discussed. Here we are just taking the first n lines and give it to the machine 1, next n line give it to the machine 2, and so on. All right, great. So the problem here is that doing such a job would require a lot of engineering. So Tuhin's question is not creating the chunks are sequential? Are we making parallel? No, we cannot create chunk in parallel. All we can do is avoid scanning the file again and again. Okay. So if the file is stored on a single machine, then that is one big problem. In case it is on multiple machine, the way HDFS do, then your job is already done. All right, and that is one property of HDFS which 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 MapReduce takes into profit. All right, so there was two problems with the external sort. First, it required a lot of engineering. Second, every time we have to do the job, we had to slice the data and send the chunks. Okay, we had to scan the data, slice it, and send it across the network. What if we could just use the data is sliced by HDFS into chunks? All right, so that is where the MapReduce comes into play. And how do you do that? All right, I'm sorry, I have got a message. Oh, okay, Arun is not able to connect. I'm sorry. I'm sorry. Okay, but I can't help much right now at this point. I'll get into the details more. Okay, but I can't do much right now. Okay. All right, he can watch that video. Great. Now, so we laid our ground on external sort, why to divide data and how to divide data. And in case of HDFS, the data is anyway divided already. So how do we? So we need to convert most of our problem into an external sort. Okay. So what is MapReduce? It's a programming paradigm to solve a big data problem, specifically for the sorting intensive jobs. and you have to code two functions. First is mapper and other is reducer. Okay, so this last one is what we call external sort, where we send our files to the external machines. Generally, when we used to do external sort earlier, it meant that we are using hard disk to do that, but external sort is also. Okay, so Ajay Karthi, why external sort was even required when we want count, right? Because we, as we talked about once again, so we had this memory problem. Yeah, hash map was taking too much of memory, and in case you divide the job into small chunks on the same machines, so let's say the memory was not a problem, but the disk became the problem, right? You have lot of hard disk scans again and again, processor was taking too much time, and then and that is why you wanted multiple machine to help you, and that is where you divided. You were able to solve problem in all these cases. First case was simply using hash map. There the problem was that RAM became bottleneck. So you divided into small chunks. So you processed a small chunk at a time, and then do all the sort of stuff on the same machine. But still, it became insufficient with respect to time being consumed. So you utilized multiple machine using external sort. All right. Now, problem with external sort is that first, you have to transfer a lot of data. Second, it requires a lot of engineering to do that. And we don't know the performance by each of the machine. We don't know how much time it is going to take for each machines. In multiple machine, HashMap was sufficient, yes. So why sorting in individual machine? No, sorting was done on the multiple machines itself. So sorting is being done at multiple machine 1, machine 2, and so on. Okay. Why? Because when the user is going to merge these things together, if these things are not sorted, then how will it going to merge? Okay. And we don't want to, scan a file 26 times and then divide all the words starting with A to machine 1, B to machine 2, and so on. There are multiple reasons for that. First is we are not sure about the load. Okay, we are not sure about number of words starting with A. No, the problem is why do we want sorted? Because we want to merge, because same word could exist in machine 1 and machine 2. All right. No, if you are again sorting them into the main node, then you are again to the main problem, right? How do you sort such a big data onto the single machine? All right. So your question, first of all, let me just go through the question. Is anybody else having the same question? Okay, okay. So it could have been beautiful that we got a same word on a single machine. All right. Say, like in this example, Ray is one here, Ray is here. Okay. And then if you have to merge it again, how are you going to do that? Okay. How are you going to do that? Right? Either you create the hash map again and do the same operation which you were doing earlier, okay, or we could again sort all of this data and then try to do unique C, but that doesn't solve your problem, right? If this data is sorted, if this data is ordered, then your life becomes very, very easy. As I explained the in an example, so all you do is keep a pointer here, keep a pointer here, keep on checking whether they are same or which one is smaller, and then you keep on counting. So the okay, yes. Machine 1 gave us the count of a subset, machine 2 gave a count of subset. So these are not subset completely, unique distinct words. A word might exist, same word might exist in one and same might word exist in two. So the user has to just sum up all of these. Yes, but think about that each list is 10,000 words long. All right? 10,000 words long. Okay, and I mean, these two lists can have a lot of things common and also a lot of things different. Now, how do you merge them to bring a single list? Think about it. You got two lists, each with different set of names and their frequencies, different set of words with the frequencies. They can have a common words as well and different words as well. Okay. Actually, Arun is facing a bit of problem. So just think about it. You can frame your question by the time I answer Arun. Just give me a minute. All right. Just give me a minute. Class is getting over in few minutes. All right. So we have got how many minutes? 50, 25 more minutes left. All right. And no, I'm not getting this. Okay. Output of machine 1, RE2, and output of machine 1 is RE2 and SA1, and output of machine 2 is GA2 and RE1. Yes, yes, right, right. So, okay, okay, let me to get this info. Machine 1, machine 2 can do hash map, right? Then, yeah. So, if the input, if the two lines if the two lines are sorted already, then it becomes easier. I don't know how what to do, man. Okay, okay. So Ajay, I think I think we should let me just one more time I'll explain, and then we can discuss it offline, and then we yeah. So basically, his point that we can happily use the hash map again, and then solve this problem. The problem is, again, if you are using hash map, so where do we want to use hash map? At the here or on these separate machines? Machine 1 or machine 2? Where? Separate machine, right? Now if you do that, if you do separate machine hash map, what should be the output? Should the words which you are outputting be ordered or should not be ordered? Should not be ordered. Let's say they are not ordered, but output of machine 1 and machine 2 may have words in common, right? They need to be summed up together, their frequency need to be summed up together, right? Now how would you do that merging at user level? Here. Okay, great. Now if you do that merging, becomes life becomes easier if the two lists which you are trying to merge are ordered by default. Okay. No, this is a very genuine question, and I wanted to answer because other people would also be having the similar doubt. All right. Now we talk about MapReduce. It is to help solving such kind of big data problem. Okay, and think about all the words existing on internet. Okay, the petabyte of text, and you want to understand that the frequency of word, how it is changing over a period of time. So similar kind of problems could become very intensive, and specifically for the job which are sorting intensive. Or you can convert your problem into a job where sorting can help you. The way sorting helped us just now in merging two lines to list of words. Similarly, sorting can help you in infinitely many ways, like doing a binary search over sorted data. If you're imagine your dictionary which you use at home, the words are not sorted. Can you use it? No, right? It becomes impossible. No matter how you organize it, it becomes impossible. So sorting solves a lot of problems, and most of the problems in the real life can be converted into sorting. And MapReduce solves the problems which are sorting intensive jobs. We would have to create a function called map, another called reduce. Okay, and I mean, we also call them mapper as well, and reducer mapper, or mapper reduce as well. So both are used interchangeably. Okay. So convert input into key value pairs. The mapper's job is to convert the input into key value pairs, while reducer job is to aggregate values for the key. And this aggregation, this collection, how the bunching all the keys together, all the same keys together, but all the values for a key together, is the job of Hadoop. All right. And MapReduce is not only limited to Hadoop. Now lots of people have taken the inspiration from MapReduce, such as MongoDB, CouchDB, and other systems. And mapper and reducer can be written in any programming language. And your normal binaries, like uh, your Unix binaries, say /bin/cat/ls, everything, or any of your program, your Perl script, and any other program, you can be used for the mapper and reducer. Okay. So Ajay, just make it public. Don't have to direct it to me. It could be improved at machine level by counting and sorting keys. It could be improved at machine level by counting and sorted keys, then sorting and counting keys. Right. You got it right. Okay. All right. So mappers and reducer can be written in multiple kind of languages, and then here is the actual dynamics, how it happens, the map and reduce. Okay, how it happens. I will take some time. Same problem which we earlier faced. Now imagine that, imagine your code. So this function of map and reduce, you see here. Okay, what it does is whatever input line you are given, sa, re, saga, is converted into sa1, re1, sa1, ga1. That's the job of mapper. Mapper converted your input into an output. Okay, and here one is just a placeholder. Okay, one is just saying ki, its frequency is 1. Now this function, if you do not understand any of this, okay, do not mind, just think about input and output. All it did was took each word and converted into key value pair, word space a number. Here it's just 1. And then what MapReduce will do is this job. You see this dashed line, it took this data of yours from multiple machines. So this mapper is going to get run n number of times irrespective of your choice. Okay, so the way this chunk exists, it could be existing on multiple machines, similar chunk, and everywhere this is the table, this is the kind of table it is going to generate, where the word space 1, word space 1, and so on. All right, now right. So here what is happening is, before we started this whole process of writing MapReduce, I mean handing over to the MapReduce, we said this is our map function. This is our reduce function. Okay. And all this map function is doing is breaking this line into word space 1, word space 1, word space 1, and so on. And then your reducer's job is to aggregate, sum up these values which have aggregated together. All right. So here this dashed line is the job of the MapReduce. MapReduce or the Hadoop will take your output, okay, and sort it and group it. Okay. MapReduce will just take this input and sort it and group it. So word followed by 1, word followed by 1, word followed by 1 comma 1. It formed an array, it figured it out. All right, and this ordered it. GA comes before, then RE, and SA comes before, after the RE, and so on. Now your life becomes very easier. For each of this line, your reduce function will get executed, and whatever you wish to do, you give out your output. Okay, here this line will basically, the Hadoop has merged all of the outputs of map and given it to reduce, and line by line it gets executed. Now here your job of reducer is take each word and whatever the values are there in the array, whatever values are there in this array, it will basically sum them up. Okay, so sa becomes 2 and re becomes 1 and ga remains 1, and so on. So similarly, or basically if you look at the next screen. Right, right. So when we are, so similarly, this is the same code. Here you look at your map code is doing nothing but taking each word from the line, printing it line space 1, line space 1, sorry, word space 1, word 2 space 1, and so on. Okay. And your reduce is only doing for each line for each key or each line, it is just summing up the values. All right. Now you look at the multiple node scenario, same problem as we solved earlier. We have, so before starting MapReduce, we tell MapReduce that our file exists in Hdfs. So this is one chunk, this is another chunk. So the job executor or Hadoop figured out that there are two nodes, node 1 and node 2, which are near to this data. And hence, your mapper code will go to node 1, your same mapper code will go to node 2, and the same operation which happened on the previous screen happen on both these nodes. And what is happening? The output at 1, okay, the one is this, okay, you can think of here one, I have marked these stages as one, and what is there on the each stage is listed down in these tables. Now at the stage 2, what will happen is it will convert this data into this form, okay, and this is your function. You are deciding how will your output look like, what will be your key and what will be your value. That is decided by the map, and the code is being written by you, okay, when you are writing map reduce code, right? So the output of first mapper is this, second mapper is this, okay. Now this is taken by sorting on both the machines and it is converted into this, all right, here, and then it is merged together in the fourth stage. Fourth stage, the data got merged together, and in case there are multiple reducer, generally there is only one reducer, okay, there is only one reduce by default. It is up to you to divide or reduce, okay. So after that, this is what is happening, okay. So it merged this data together and ordered it. And after ordering, it splitted the data again such that all the keys with the same, all the same keys remain together, right? And still divided. So assay went, all the four assay went to the second machine. And hence, this is the output. Assay has four occurrences as, and GA has one and RE has two. Okay, so this is what is the machinery happening. All right, so so Tuhin, your question is answered, or should I repeat? So these are already stored in HDFS. Okay, this data sa re ga and sa re sa, these are the two lines from different HDFS file, or this is actually huge text. I have just kept it very simple. There are multiple lines at both the places. Here Hadoop figured out node 1 and node 2 are very close to this data. So it sent your map logic, whatever you have written in map, sent to node 1, and same logic replicated to node 2. What did this logic did? It took this line, converted into word space a number 1. Okay. And similarly on this one also. And Hadoop did a merge and shuffle. Hadoop brought first it did the sorting on each individual node and then did a merge and then again splitted the output into two portions, reduce 1 and reduce 2, and here your reduce code is being executed here and there you get the results. So I know a lot of people have doubts. Feel free to ask those doubts right now, because those doubts will become huge after some time. This is important, very important. Basically, here I'm trying to demonstrate that your map logic is being executed at multiple places. The output of map logic is merged and sorted, merged and then splitted by Hadoop. Okay. So generally, to bring down the complexity, you can imagine there is only one reduce and the data is not splitting after this. So Gunjan's answer is the question is that do we so if you have multiple reducers, we don't have uh, we do not do we not need a grand reducer? Yes, do you do? Okay. Okay, it all depends on how do you want to do your programming. Okay, right now for the case of simplicity, I have kept this. Okay, I will just close some of the things. Okay, yes, you got it right. So map combine reduce is this process. All right. So can somebody if somebody is having doubt, just please let me know, because I want to make sure that everybody is clear about it. Okay. Basically, the whole idea, first idea was to divide the data onto multiple machines, onto HDFS. Second idea was how do we process this data such that both the jobs are done. Our divide and conquer can really work. And this is what a divide and conquer is. We divided the processing, we divided the data, and we are happily merging and giving out the results. And all we did was we just wrote a simple function to create mappers which convert your input into key value pairs. And then we wrote a reduce function which takes the same value and then uh, combine them together. All right. So this is what a map reduce in general is. Okay. So let me go ahead. I have a lot of things to discuss. Now the other analogy you can take with map reduce is you the group by. Okay. Okay. So Arun is actually not able to connect. Okay. So what should I do? My assistant is not here. Okay. So we can have a separate discussion after you watch the video. Okay. Okay, because he's not able to connect and he's little restless. So I'm asking him to basically have another session, a tutorial session. And okay, if that happens to with any of you, you can do the same thing. In these cases, I mean, these are very special case where he's not able to connect again. Looks like they are having an outage, the webinar guys. Okay, so he's not able to connect. Never mind. So again, map reduce paradigm. Now, when we talked about map and when we talked about reduce, note that the job of map was to identify the key for the aggregation. Okay, job of the map was to identify the key for the aggregation and the value for the aggregation. Okay, it is similar to the group by clause where select word and then from table group by word. Okay, okay, and I don't know how to shut it. Okay, okay, never mind. So select word and then aggregation from table group by word is the duty performed by mapper, while the reducer is this way. Okay, so this is the big analogy you can think about when you think about mapper and reducer. All right. So identifying the key and the value is the duty of the mapper, while combining those values together for a key is the duty of the reducer. Now, I want to leave the class with few assignments so that you guys can think about problems again and again. Okay, we'll discuss in detail more and more about these problems, and then as we come back, we will discuss more about these problems, and so that you can think in terms of map and reduce. Okay. Now let's talk about the another problem called frequency of letters. All right. So computing the frequency of the letters only, we just want to count how many times A, B, C, and so on till Z came in the text. Okay. Do we need MapReduce? If so, when? How big our file should be? Okay. So these are the assignments for you guys. Think about all these assignments and come back when you have, if you have any doubts. Okay. We'll discuss in detail all of these, but I want to describe each and every problem right away. All right. Second problem is, if you are given a very huge text, just like the one we just talked about, how would you find the anagrams? An anagram is all the words which can be formed by rearranging the letters of the word. Say cat, take, act, all are the anagrams. All right. So you find the anagrams in the Hughes text. You need to report that these are the words which are anagrams of each other. If there are not anagrams, all you need to do is just print one single letter per line. Okay. So in other words, you can combine all the anagrams together as the result of this program. Okay. Third problem which I want to ask is, imagine Imagine that we need to find out people from a same family, and let's assume that people who are from the same family are either having the same DNA or exact mirror image of the DNA. All right. So here the input is user 1 and DNA of the user 1, user 2 and the DNA of user 2, and so on. Okay, now here you have to report that user 1, user 2, user 4 are belonging to the same family. Okay, they belong to the same family. Why? Because user 1 and user 2 are exact mirror image of each other, while there, if you see ACGT and TGCA, they're exact mirror image of each other. So user 1 and user 2 are from the same family. Similarly, user 4 also belong to the same family because it's exactly same ACGT ACGT. So all the people whose DNA is either same, exactly same, or are mirror image of each other, then they belong to the same family. No, Gunjan, this is not the same one. In the second problem is different. It's any arrangement. It's a cat, take, act, any arrangement, not the exact opposite one. Okay. So here we're talking about exact opposite or identical. All right. So we have to bring all those, you guys cluster all those users together to find out the same DNA people or people from the same family. Okay, so these are the three problems, and the fourth one is a very interesting problem. Okay, fourth one is, imagine there is a country, and in each country the voting is not equal. Okay, the vote count is not equal. Unlike the ideal democracy where everybody is equal, in this country people's vote matters more if they are richer. Okay, so imagine such a country. Okay, now they are voting each other, these people are giving votes to each other. All right. So A voted for C, B voted for C voted for F. Okay, if you see the first table, A voted for C, B voted for C voted for, sorry, yeah, C voted for F. Okay, so these people are voting for each other, and this is second list is. Hi, welcome Arun. Finally, you are back, and I'm really sorry for this. Okay, so in this country, let's repeat the problem again. In this country, the voting is not really democratic way, where everybody has got equal voting right. In this country, the voting is based on how much is the bank balance of an individual. Okay, so you are given a list of people and their worth. A has got 5, B has got 1, C has got 11 worth. Now, when people are voting for each other, now at the end of day, the vote is being counted as sum of total worth. As in, now the person A, nobody voted for person A. His vote count is 0. Person B, nobody voted for person B, and hence his vote count is 0. But person C was voted by A and B, and his vote count is 5 plus 1, 6. And similarly, person F was voted by C, and hence his vote count is 11, and so on. So this way, you have to, given these two lists, list 1 and list 2, worth of the people and the votes, you have to tell the actual vote count at the end of the whole counting. All right, so this is the fourth problem. So do you have any doubts with respect to these problems? Basically, you will have to come up with not the code but just a plan, that what does your mapper will give out, what does your reducer will do. The way, in case of word count problem, mapper broke down the line into words and printed out word 1, and then against that one, then numeral 1, word 2, numeral 1, and so on. Okay, all right. So guys, if you have any questions related to this, let me know right away. Okay, maybe I did not explain some things properly. Okay, we'll dive into details of each one by one tomorrow. But you do your homework, go through all these four problems. First one is find the frequency of letters in the text. Second one is find anagrams. Anagrams is rearrangement of the word, letters in a word. Okay, and then find the DNA sequences of the people who belong to the same, find the people who belong to the same family. People who belong to the same family are either identical DNA or exact opposite DNA, exact mirror image of the reverse or the mirror image of the DNA. All right, ACGT and TGCA, they are exact mirror image of each other, and hence user 1 and user 2 belong to the same family. Okay, now you have to come up with a scheme that in case I convert this into this map and this reduce, I will get this answer. Okay, you have to bring these two users together based on forming a key, such that when I sort this data, the people from the same family come together. All right, so these are the four problems. Think about it, prepare the plan as in terms of what will be the output, just in any natural language. You don't have to write a programming or code for this. You just tell me that these are the steps. What will your mappers do and what will your reducer do? That's all. That's all. And in case we have a doubt, let me know at any point of time. All right, guys, that is pretty much for today. If you have any questions, feel free to connect. Okay, thank you, Tranmin. And yeah, same session, it will be on the same session tomorrow. Okay, same session, same time, 7 a.m. to 10 a.m. All right, IST, we are talking about IST, not for no, Tranmin and Jimmy. Please note down the time for your Yeah, it will be the same time as today, and we'll be talking on the session number 3. So the assignment. So this assignment is also available. Can you, Jimmy, were you able to log in? You will see this kind of page if you log in. Okay, if you log in, you will see this kind of page. Here in the session 2, I will enable the installation instruction and other things, required things. Okay, so video will be uploaded here. So keep an eye here. Maybe in a 15 minutes of the time, this presentation will be available. Okay. So you will see on the, if you log in to the web page under the session number 2. Who is not able to log in yet? Okay, great. So go through these 4 problems, think about all the 4 problems, and think about the strategies you will use. Okay, and in case you get stuck or you are not clear about a problem, just drop me an email. I'll try to answer you as quickly as I can. All right. So you don't have to code per se, but if you code, then it's even better. But a plain English will be sufficient. All right. There's no deadline for the quiz right now, but the I mean, you should finish it. You should finish it before the next Saturday. Okay. First quiz you should finish by next Saturday. Okay. In case there is something wrong with any question, then also just drop me an email or leave a comment then and there. Okay. Okay, then that's pretty much for today. We'll see you tomorrow morning again at the same time. Bye bye. Have a nice time. Okay. Hello. Am I disconnected? Okay. Bye, Tuhin. Okay. Go through these 4 problems, think about them, and you should be able to solve these. And I hope that you should at least attempt 2 problems out of it. Thank you, Gunjan. You to have a great time. Bye, Vijay. Bye, Arun. Okay, Arun, go through the video and then have a look at it. Bye, Karthik. Ajay. Okay. Bye bye. Have a great time. Bye, Jimmy. If you have any questions, just drop me an email. I'll try to clarify as quickly as I can. Okay. See you tomorrow. It's the same time, 7 a.m. to 10 a.m. IST. Okay. Okay. Bye, Jimmy. Bye, everybody. And have a great time. Have a great time. Bye bye.